Okay, let's do a brief review of what we covered on Monday. It's basically asymptotic complexity. Only thing that I will be emphasizing is those definitions that we discussed. Two important reasons. Again, you want to compare. 죽겠다 정말. 그죠? I wanted to use this computer, but this USB also doesn't work. I don't know how the other professors doing their stuff. The others using this computer to do lecture? USB로 꼽아서? Why mine is not working all the time? 왜 나만 안 돼? USB 꽂으니까 안 되는데? Something is not right. Basically, we wanted to compare two algorithms or methods, programs. What is asymptotic complexity? My term, like I said many times last time, n go to infinity. N really big. I don't care if n is small. N is small, those rules may not apply, but n is large. Assuming n is large, something goes to extreme, then what's going to happen? If that happens, what's the complexity going to be? That's asymptotic complexity in simpler definitions. n이 미친 듯이 커질 때 어떻게 될 때? I like to find out the boundary, right? Hopefully that is a bit more easier explanation like this. Predict a growth in runtime as instance change characteristic changes. N changes. What's going to be, how long does it take? Let's predict the runtime if we can. Asymptotic complexity provide a meaningful statement about the time and space complexity of the program. But like I say yesterday, Monday too, we don't care too much about space complexity at this point. And next slide will tell you why we don't care too much at this point about the space complexity. And then I will show you this. I show you this examples, blah, blah, blah. Basically, it's inequality equations. I give you a set of inequality equations. Inequality equation이 뭐지? 등식이 아니라 부등호 돼 있는 식. We did that, right? It's all there to calculate the range of variables that satisfies the condition. 그죠? So you guys done this when you guys in, I think inequality equation nowadays, the kindergarten kids are doing it. 아마 1학년, 2학년? So things like that will appear most likely in your assignment and exam as well. So be prepared. I mean, you guys know. And notation, big O, omega, theta, little o, but what did I say about omega? Theta and little o. It's okay for now for us. Big O and omega is a bit more important for us. Actually, big O is most of our interest. And theta, we already know it's something in the between that matches, that stays in the between big O and omega. If big O and omega have the same notation, then we can say the theta also have a same notation. So, what was the example on the next slide? Order n square, and some sorting algorithm says order n square, and then they also analyze that their minimum time, minimum bound, lower bound was omega n square. So they naturally says that that sorting algorithm is a what? Theta n square. We can say that, right? So little o, it's a bit loosely upper bound, so we don't care too much at this point. So average case, upper bound, bubble sort. We try to discuss different examples for try to give you ideas for worst case. Don't worry about too much in average case in this part. I had a few questions right after the class on Monday. What is the average case to be exact? They also mentioned in a few slides after. It's like this. In the simpler terms, I have one algorithm. I'd like to know how they perform in general. So I can try with the data set with the size 10. I was also wondering if the data size is 1 million. And then I try something in the between 10 and 1 million. 5, what is the middle of the 10 and 1 million? I don't know. 500,000, something like that. 500,000. Yeah, I guess. So I try that. So you try few numbers maybe in random order and calculate how much time it takes for each data set. You add them up, divide by number of times that you use those data sets. Then you got an average case. You have a rough idea of how long it will take. So that is a simpler concept in average we're discussing in this class. It is also related to a bit more data notations. So upper bound, blah, blah, blah. We did this in sequence. How do you look at it? And there was a famous definition Fn equal to big O of G of n. If and only if, what was if and only if again? You can go both directions, right? When you try to prove something. If and only if positive constant C and n0 exists such that Fn is less than or equal to C times G of n for all n's. Okay. Whatever that means, memorize, memorize, memorize. I don't know how many times I have to say it. Typical example that you can use was whether that's certain function. When I say function, it's the same thing as time complexity of an algorithm, okay? Function, linear, quadratic, or exponentials and stuff like that. Maybe we can look it up one by one on the wiki. I always telling you that wiki is much better than I am. I mean, basic ones are much better. So something grows quadratic at most. That's why you can say its upper bound is quadratic. So order n squared, blah, blah, blah. Order n is a set of functions that grows at most linearly, straight line with certain degrees. Order 1, you can say any number, constant number there, set of functions that is bounded by a constant. We draw those pictures on Monday to show you what they try to say. And n to the k is set of all functions that grows polynomially. N to the square, n to the 3, n to the 4, well, 3차, 4차, 방정식, like those stuff. So those are called polynomials. Who actually start reading in 3.1 and 3.5? No. Because we're going to cover chapter 4 today. So 1, 2, 3, 4 in 2 weeks. 그죠? You should be start reading your textbook. So again, simply verify what I say in class is what they say in textbook. Okay? 그죠? 읽을 거 많다, 그지? That's 1 to 4. 1 to 4. Lower bounds. Once an algorithm for solving specific problem is found, question arises whether it is possible to design a faster algorithm or not. My explanation on this part was if we have a proof that certain algorithm cannot be done under some time, why not you're spending your time on developing something is not possible. So certain sorting algorithm, all of the sorting algorithm, I think in the textbook they say the minimum bound is n log n. Do not try to come up with the sorting algorithm that can do a linear time. It will waste your time because there is no such algorithm exists as far as we know. So that is a job of a lower bound, what they try to tell you for the omega functions. Certain number of steps that every algorithm has to execute at least in order to solve a problem. Sorting n numbers, n is 4. That's a simple example. If you need to sort n numbers, what is the minimum number of steps to do it? I mean, at least you need to look at all n numbers for once. It might be minimum. So that's a minimum boundary, but they didn't say omega n for sorting algorithms yet. Same, you just change the direction of those inequality signs, and you have already memorized a big O. Omega should be okay. Omega should be okay. 아직 외운 사람도 없겠지, 그죠? Faster is better. Faster is better. And omega example is just to try to show also another example of solving a well, this equation is exact same replica of the definition itself. So they just plug in the numbers, just try to show. They satisfy this condition, so I can say Fn is omega n. Definition하고 똑같아. 숫자만 바꿔서 넣은 거예요. 그렇죠? So you should be able to do this. I give you one problem, maybe a proving question, like these ones. This also proof. They also show that it satisfies the definition that we memorized for omega. So we can say that something is omega g. So I give you one formula. I give you maybe a constant values to use. And then you don't know how to begin. One of the easy stuff. The reason that I ask you to keep memorize the definitions is just simply plug in. Plug in. And you do a very simple mathematics. Whether that inequality signs satisfies, done your proof. I guarantee you your assignment will ask you something like that. And many of you will not know where to begin. But I already told you where to begin. Those definitions is a starting point. Okay? 나도 그랬어. I was also doing the same thing when I was you guys, taking similar course when I was in university. I had no idea how to write an answer for the midterm solutions. So I just memorized the definitions. I start writing down. Still get me a 50%. I still got the partial mark. Okay. This example function and fn lies omega of n squared as well as in order of n squared. Then they start introducing the theta n squared. We know this. At this point, you know how to define a theta functions as well. Something stays between part. So it is above and below. It's very obscure, above and below. But it's not exact. 그죠? Something is a bit obscure, but it should be okay at this level for now. Someone asked me last class, is theta notation is a bit confusing. I said, yes, it is. Because in order to study a bit more amortized cost later, theta requires much more advanced courses later. I mean, it's natural that you're having a difficulty, but keyword, above and below, that's probably good enough for us at this point. Plus, we know how to draw a graph. I show you how to draw a boundary functions between, and then you can assume that's can be told as omega functions, theta functions. Keep confusing, omega, big O, theta, little o. There are other notation too, but I hope we don't use it in this class. Theta examples, I mean, simple as they try to come up with the heap sort. Okay, I think I explained it last time. Constant log base 2 to n, I mean, logarithmics growth increase slowly compared to the problem size binary search. 그죠? I explained this last term when many of you have taken Introduction to Computer Science. When you see a binary tree, and then if I start asking you about the runtime on the binary tree, what is the natural things to expect? Runtime. I mean, everything is either 0 or 1. So when you make a choice of 0 or 1, you're also running into, it means you just discarded half. So your problem searching space reduced to a half. 그죠? Also make another decision among that half. So you discarded half of half, half of half. Natural that we assume that log base 2 of n. 그죠? log base 2 of n. 근데 뭐 log base 2 of n이나 log base 10이나 뭐 그래프는 뭐 이렇게 되나 비슷하죠. 나중에는 그냥 로그만 쓸 거예요. 그럼 대충 그냥 로그 베이스 10인가 보다 쓰면 돼요. 특별하게 여기에 2라고 써놓지 않으면 그냥 로그 베이스 10이에요. Linear. No. N times log to the n. Typical sum divide and conquer approaches. Divide and conquer. 뭐지? Sorting examples are good example for this divide and conquer. You divide a list into half, you sort, and then you merge it later. So every part they sort, each part they've been sorting, they merge. When they do a merging, do another sorting, make things a bit faster if you can. So that's why they say n times. So you do 이건 나중에 나오는데, you do a sorting of a one party in log n times. I will explain later when we discussing this sorting times. N square and n to the 3 and cubic and 2 to the n exponential growth is extremely rapid, possibly impractical. So don't even try to come up with the exponential algorithm and try to write on your computers and run it. If n is too large, you may not be able to do it. I mean, it's slow. Your computer will spend a lot of time to compute that. So practical complexities. And still, I know some people are still confused. What is n? And if you start plug in the number to an n, it might be easier for you. N, let's see, n grows, log 2, n, 뭐야, n. Yeah, 1, 1, 1. If n is 1, 2, n is 2, 2 to the 2, 4, 8, n goes to n, 1, 2, 4. This number, I mean, up to this part, we're okay. I mean, even some numbers are smaller. 2 to the n is smaller than n to the cubic. That's why the lower part of the curve doesn't representing this asymptotic complexity properties when n is large enough. You can see that numbers are not extremely large, this exponential growth. Assuming this is a second, say something takes 1 second, 2 seconds, 4 seconds, and then this is algorithm to do it. It takes a lot of time to do it. So it's one simple example of n goes large. N is just 32. It's not even large numbers, but still exponential functions are. I can't even read the numbers. 그죠? So they show you how to compare this complexity, how important this asymptotic complexity representations to show you this type of stuff. So what might be the natural questions to ask? What might be the typical questions to ask in the exams? 뭐가 있을까? Maybe I give you these functions, big O notations, and ask you to order it. Fastest to the smallest. Don't care about the other numbers, but big O notations. 섞어놓으면 찾을 수 있을까? If I mix it up, can you actually order it together? Overly complex programs may not be practical given the computation power of the system. Overly complex programs, like programs that have exponential runtime, even for cubic, may not be suitable for your PCs to run it. cubic runtime 되는 게 뭐가 있을까? I don't know. 3D matrix multiplication, maybe it's a cubic. Try to do that in your own computer with your own program that will be slowed down. Of course, there are other programs that you can use, optimize those matrix operations, make it faster and less memory. But if you try to do it by yourself, you will run into trouble. So bottom line, again, read chapter 2 and 3. Chapter 2 and 3. But I kind of went a bit fast. I was assuming that most of you have this background last term, so shouldn't be that difficult to swallow at this point. 다 한 번씩 본 거잖아, 저번 학기에. 그죠? No, yes. Again, no replies. 나를 죽이세요. 힘들어요. Performance analysis. Now it's performance measurement. Same thing. It's a continuation from chapter 3. Perhaps a bit of less complexity, asymptotic complexity symbols. Program performance. Recall that the program performance is the amount of computer memory and time needed to run a program. Recall that program performance is the amount of computer memory and time needed to run a program. So far, when we're discussing time complexity, we actually didn't consider any memory access time and stuff. I mean, those memory time access also have other issues when we try to determine the total time complexity. So we'll take a look at it briefly. Analytical performance analysis, experimental performance measurement. I can say analytical is something to do with your pen and pencils. I mean, the ones that we just saw, asymptotic complexity. You don't need you don't need to run a program actually. Just take a look at the code, find out the frequencies, and you add them up. You might have it, and then with that numbers, you can certainly start calculating a asymptotic complexity and the boundary values and stuff. But experimental, I'd like to know in numbers, actual seconds, milliseconds, how long it takes. What is the main impact? What is the main impact from which party? Memory access or CPU computation? What's the issue? Performance of program depends on the number of types of operation performed and memory access patterns. A lot of stuff is coming from the last terms and introduction to computer science. I still remember I was in this class, in the same room when we discussing the CPUs and stuff. We went to a website, of course my favorite enuri.com, and try to look at the CPUs and how much they cost. 기억하는 사람? Only I'm remembering those stuff. We look at the CPUs and why certain CPU is much more expensive than the other one. It seems to be almost same spec. Because of the cache memory, they say some CPU has, I don't remember the actual units, megabyte, kilobyte인가? 뭐 이랬지. I don't remember the actual name. I don't want to go to Enuri, taping Enuri. Doesn't sound right. 수업하는데 갑자기 enuri.com 들어가서 뭐 검색하면 보기 안 좋겠지, 그죠? Anyway, those memories, large memory to the CPU, close to CPU, L2 cache, L1 cache. If you have those cache memories, then CPU much expensive. Why? Because they are faster memory. I said that in last term. Same thing. Those memories are expensive because they are faster. So depends on the memory access patterns. We need to compute the running time complexity according to that as well. You do not need a working computer program or even a computer. That's why I don't ask you to bring your own laptops for the midterm for performance analysis, right? Some use of performance analysis, again, is comparison of different algorithms for their time complexity. Why do we want a performance analysis of algorithms? To determine practicality of the algorithms. I mentioned this a few times, but what is practicality of the algorithms? Do not try something that your computer cannot take. Before you try, we can tell this program will not be suitable for your own computing resources. So whether that's actually practical or not. Lower bound, maybe. Lower bound or upper bound as well. To predict a runtime on large instances. N goes to infinity, large instances. To compare two algorithms to have a different asymptotic complexity. I mean, at some point, this one might be better if N is within the boundary of this one always better than linear. So that's another comparison point for that part. Limitations of performance analysis. Does not account constant factors. Those formulas, polynomial equations that we try to do. I mean, who knows? You can have it's still a n square equation, order n square equation, but at the end it has 1,000 times n. The constant value is too big, then they kind of interfere of the overall performance analysis of this asymptotic complexity. 예를 들어 방정식이 있는데 뒤에 n 스퀘어, 우리 지금 n 스퀘어만 중요하게 보잖아. 근데 뒤에 붙어있는 n 붙어있는 곱하기 값이 1000, 10,000 이렇게 되면 실제로 그림을 그려보면 초반에는 좀 영향을 미칠 거 아니에요. 원래 이렇게 봐야 되는데 막 이렇게 된다거나 그런 경우를 얘기하는 거예요. Like these ones, the constant factors may dominate 1,000 n times versus n square. I mean, 1,000 n is still order n, but when you actually try to do this, 1,000 n would take much longer time than n square within the boundary of certain numbers. Especially if we're interested only in n is less than 1,000. Modern computers have a hierarchical memory organization with a different access time for memory at different level of hierarchy. L1 cache, L2 cache, your main memory. Sometimes your hard disk nowadays have their own memory too. So hierarchical memory stuff. Tree, hierarchical again, they have a structure in it too. ALU, 뭐야? Arithmetic control units that we covered in the introduction to computer science. A lot of stuff is coming from the introduction to computer science. 그죠? No. Who actually burned that book after the course? 책 태워버린 사람. 아직 가지고 있는 사람. 누구 줄 예정이다. 없애버릴 예정이다. 그냥 기념으로 가지고 있어요. So if you have a difficulty, just think of it as a CPU. CPU right next to CPU also has a register, something called register, that is a fast memory space. When we discuss those assembly and machine languages, we use those registers to store in and take a value out, right? Those are also memory space that we mentioned. Register. C is a CPU cycle. CPU cycle. It's like a unit of a CPU. It's like a unit of time for CPU. So if in my program to run it, it needs maybe 100 cycles to finish my program. So I take a CPU time for 100 times, if you want to think it that way. Let's see, CPU cycles, one CPU cycles to access register memory. L1 cache, another also fast memory right next to the CPU. It takes 2 cycles below. I guess this is the size of a memory. I think it's much larger, more than CPUs. 32Ks, 512Ks. Main memory 512. I don't know. Nowadays 512 is the minimum requirement for Windows installations. 아니다. minimum requirement for Windows installation is 기가? 한 2기가 되지 않나? But they only takes less. Even Windows 7 they takes maybe 600 to 700 meg less than that. Notice that 2 CPU cycle, 10 CPU cycle. In order to access the memories that you have in your computers, the things that you can buy with a cheap price, 100 cycles. This shows you how much time they take for each memory access. The program interact with these memories to do it. I mean, sometimes they ask for something from L2. Most of the time, they take something from main memory. So what do? You just number of times that main memory get accessed, maybe 5 times, 100 CPU cycles. Only twice for L2, 2 times 10 CPU cycles. You add them up, you have a rough number on total number of CPU cycles that you require for your program to run. I mean, in order to program to run, you need to access the memory anyways. So that is a memory hierarchy design, and hopefully you can see that why it takes a different time for each type of memory. Read section 5.1, 5.2. I think I take a look at it before the class. It's not much. Just try to give you very general information on cache memories and main memories, which that you guys already know. 이러다가 오늘 챕터 5까지 가야 되겠다. How many chapters do we have in our textbook? I forgot. Huh? 19? Oh, there's a long way to go. I mean, first few weeks, we'll be covering maybe 2 chapters in a single class, but later we'll be covering a single chapter for 1 week or more than a week. I heard that next year's the number of weeks now is going back to 16 weeks. 그죠? Imagine your freshmen try to take this course for 16 weeks. They will cover at least 2 or 3 more chapters. Limitations of performance analysis. What are the shortcomings of this performance analysis? Performance analysis does not account for difference in memory access time. We haven't discussed anything regarding memory access patterns in big O notations and omega notations. So there is no mechanism to take care of those stuff. Programs that do more work may take less time than those of do less work. A program with a large operation count and small number of access to the slow memory may take less time. What does that mean? You have maybe a program size in terms of number of lines of code that you have maybe about 1,000 lines of code in your program. And you only have, another program takes only 50 lines of code. But the larger program takes less interaction to the memory access patterns. So the large program may finish faster than smaller program, while the smaller 50 lines of code program requires a lot of memory operation. It means takes a lot of CPU cycles. So taking a lot of CPU cycle meaning longer time to finish a job of a program. Concerned with obtaining the actual space and time requirements of a program. You actually run something in your program and try to measure how long it takes. Have you ever done that outside of this course? I'd like to know, I wrote my assignment. I'd like to know how long it takes. What might be the dumbest way of telling how fast your program is, your assignment, for example? 어떻게 하면 돼? 몰라? I actually did that. I did that once when I was in first year. I wanted to see how fast it was. I think it was also one of the assignment questions too. So I had my stopwatch, enter. Of course, those programs are so small, it's impossible to click. As soon as I press enter, it's done. It was impossible to measure. This is probably the dumbest way you can do. Dumbest way of you can do. 어떤 사람 그런 사람도 있어. 모니터에 이렇게 줄 긋는 사람도 내가 봤어. 이렇게 하고 지금 생각해보면 걔는 도대체 지금 뭐 하고 있을까 그런 생각도 드는데 희한한 애들 많았던 것 같아요. So one of the ways that you can try, the easiest way you can try, maybe at the time, within your code, at the time of execution, you print out the current time of your PC. Print out. And then when you're done your program, you also print out the current time of that PC. Then what do you do after that? You have a starting time, finish time. You just simply subtract start time from finish time. Then you have a rough time for how long it takes. Also, dumbest way you can try. They will show you why. Probably the most reasonable way as well. I don't know. And they say, read the reasons on page 122. What was the reasons? What is the reasons? Assuming that no one actually ever looked at the slide before the class. 122 probably says, I mean, it's not changing much. Compilers are nicer nowadays. Also, from the valuable declarations that we studied, those are pretty much good enough. They don't change a lot from those basic analysis. So we don't usually care. Plus, compilers are much more nicer. It's not going to change too much. And they also says in the textbook says, even if you are using a recursive function, that was an issue, right? Because it was in the stack, so it can grow. Thing is, you can actually compute quite precisely for those stack grow. So you don't actually need to consider too much for the runtime space requirement at this moment. 이건 runtime space requirement. What is runtime space requirement? 실제로 돌릴 때. So it's different from when you actually compile it. Compiling is you have object file. It's different from object size of the object file to runtime space. 오브젝트 파일을 실제로 돌렸을 때 실제로 메모리 쓰게 하고 그거랑 오브젝트 파일의 사이즈랑은 틀린 거예요. 그래서 별로 크게 오브젝트 파일 사이즈랑 크게 다르지 않으니까 별로 신경 쓸 필요 없다 그런 요지로 써놨어요. 하나 두 개 이렇게 보면. Read page 122. I'm sorry I keep speaking Korean, but I explained it in English before I said it, so it should be okay. Should be okay. It's fun, 그죠? The textbook tells you a lot of stuff that you never thought of. 재미없어? If it's not fun, you should let me know at the beginning of the term. Or I would just continue this way until end of the term. It would be a nightmare for all of us. 재밌잖아. 하기야 이게 재밌으면 정상은 아니다, 그죠? 재밌으면 정상은 아닌데. 그래도 어쩌겠어. 전공 필수인데 들어야지. Performance measurement need. Programming language, working program, and computer. Compiler options such as G++, -0, -02, -03. See the manual page for G++. How do you see a manual page of a G++? If you're running a Linux or Unix environment, man G++. Man is short for manual. And most of you running Windows, just type G++ manual from Google. It will get you the same page of the Unix instruction sets. Let's take a look. Maybe. G++ manual web page, blah, 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 descriptions. And they will probably give you the options, a lot of different options. These are the options that you can find. Honestly, I don't know all these options, but you can actually find each one throughout the web page, and like these ones. -o files, place and output file of the file applies regardless of what sort of output is being produced, whether it is executable object file or assembly file or pre-processed C code, whatever that is. And they give you explanations of each options that you can try. minus O2. The output is sensitive to effect of the previous command line option. So example, possible to find out what optimized are enabled at O2 using it. Optimized. I guess make it smaller object files if you use those stuff. Or sometimes it's even bigger than the others. So this is how you can find these options and take a look. I'm just showing you this because I know when I ask you guys, try this at home, no one's will be, so I just did it here. So you can take a look. Performance measurement need data used for measurement, worst case data, best case data, average case data. Maybe I wrote a sorting algorithm. I know that there are maximum upper bound and minimum bound of each algorithm, but I like to see whether they actually applies in the actual. I give them a very big data set, not unsorted data set, big data set, sorted data set. I like to see how they actually affect on the actual time of sorting those numbers. Will it make too much difference if it's a simple sorting algorithm on your typical PCs? I know it's difficult to see. I mean, it's just a matter of milliseconds, microseconds. So it may not be, seems to be important unless your data size is really, really large. What is worst case, best case, average case data for insertion sort, and how do you generate them? Like I say, maybe you try to use an inserting sort on a completely disoriented data set. Nothing is sorted. Might be the best, worst, best, everything is sorted. Average case, you try many of different data sets to see. How do you do this? Timing mechanism. I already give you a solution. Finish time minus starting time. And clock is a command that you can use in your, any C programming, whatever. You can also type in man clock. It will give you the instructions how to use it. System calls. Choosing instance size. Same thing applies from previous slide, best case, worst case, average case. How do you choose n to corresponding each each case? We decide on which value of the instance size of n to use according to two factors. Amount of time that we wanted to perform, what we expect to do within the times, stuff like that. In practice, we generally need the times for more than 3 values of n. Read the reasons on page 123. They have 2 reasons. I don't remember exactly. But bottom line is this. I mean, like I explained at the beginning of the class, they need a certain samples of extreme case, best case, and some random cases. So they think it's at least 3 n values should be enough. Even with each n, they do a multiple time measurement. They keep running it. So, and then they take the average out of it and then use that value for determining the performance measurement time of an algorithm. So when I say read it, please read it. It's not taking too long. Clocks per milliseconds. Clocks per millis, small number. Clocks per milliseconds. How many clocks per millisecond? 1 millisecond. Double clocks per second divided by 1,000. They wanted to see in milliseconds, so they divide that into 1,000. Clock t start time equal to clock. When they see this, they record the current time into here. Code whatever that you wanted to write. You can put your own sorting algorithm, whatever program that you wanted to do. Do it here. At the end, when you finish your algorithms, clock, get the current time of this state, and then subtract the start time. And I like to see that in milliseconds, how many clocks it requires. 아니지, 거꾸로지. 그러니까 if I do this, I will get how many CPU clocks that I had. Because in the beginning, I divide. I know that how many clocks we require per 1 millisecond. Simple. Hopefully, this will give me a total clocks, cycles that I require to finish my program or algorithm. Again, what might be the potential problem? Not a potential, it's quite clear. What is the problem with this approach? Let's say accuracy, clock. Maybe your program finished too fast. Difference between those clocks is minimal, and they usually give you 0 values, even though they take slightly different values, but time difference between the two is so small. They keep reporting you that you only use one cycle or something, a 0 cycle. So maybe that's why you do this many times, and then try to get the average value out of it. That statement just finished everything in the rest of the slide. But let's see. C program 4.1, execution time in figure 4.1. What is wrong with this in execution time? Time needed for worst case source is too small for clock to measure. Too small. I'm not so sure nowadays it's still true. In the Linux systems, when you're dealing with this networking stuff, when you're doing a web surfing, you're doing a web surfing, you exchange the data over the internet, right? The minimum time of each data being exchanged in your computer is, I think, around, the computer can track of in the unit of 10 microseconds. Might be smaller nowadays, I don't know. It depends on the operating systems. So you cannot tell the difference of those data sets among those 10 microseconds, even though they have a difference maybe in nanoseconds. Everything will be in the unit of 10 microseconds. Those type of issues also related to this as well. Clock accuracy assumes the clock is accurate within 100 ticks, cycles, if you want to say. If the method returns the time of t, the actual time lies between max of 0 to t plus minus 100, the 오차범위, plus minus 100. It says 0, but you could have 99, could be 98, could be 1. That's why I just say 0. I mean, those are the things to consider. For figure 4.1, the actual time could be anything between 0 to 100. Exactly what I described, they have in the table in the textbook, every number. Even though each trial had taken a different time, the overall time that reported from the previous program says 0, all zeros. But it doesn't mean it's 0. It could be any value between 0 and 100. Shortcomings, difficulties. So can you trust this way? If it's a long time-consuming program algorithm, then it might be okay, but if it's a smaller program, it may not be the accurate way of doing this. So repeat the work many times to bring the total time to be greater than or equal to 100,000 ticks. See program 4.2, figure 4.2, 4.3, 4.4, overhead measurement. Basically these things, like I say, they try to do that measure over and over again. So you will see a for loop in those programs, 4.2 and related ones. They do it again and again, maybe 1,000 times, less than 1,000 times, to see. What might be the overhead they try to say here? What might be the overhead here? 어디 갔어? What might be the overhead? It's very small, but overhead. What is overhead? 뭐야, 오래 걸리는 거지 뭐. Overhead of this approach is maybe clock itself. I call this function. It also takes some time to execute this function as well. That's overhead I should not be counting. I just simply want the time that it requires between this part. The time to call this clock function, taking that into consideration, whether you like it or not. So that might be the potential overhead that you might not want it to be included. I mean, if you really, really want an accurate output. Accuracy, no. After those figures, see that now accuracy 10%. First reading may be just about the change time to start time 100. Second reading, blah, blah, blah. So bottom line, finish time minus start time. But they add a certain values to provide a safe boundary, safe ground to add 100 to see it. I mean, read your programs in your textbook. 아이고, 똑같은 얘기인데, I'm sorry. I explained this anyways, and plus minus 100, those are the boundaries to do it. So, and the same thing. Please take a look at the examples on your textbook as well. So, 4.3 program, I mean, do this, exact same thing, clock, do this 1,000 times. Do this 1,000 times. And then get the average out of it. Same thing. Not much to explain here. 이런 건 꼭 코드를 몰라도 대충 알아볼 수 있잖아, 그지? 여러분들 다 할 줄 아는데 뭐 꼭 무슨 뭐 문법에 따른 거 아니잖아요. 뭐 이게 C 같이 생기긴 뭐 C 같이 생기긴 했구나. 뭐 it doesn't really matter. It's like a pseudocode style, so anybody can read this. I probably want it like this too. If I ask you any of the programming relating question in your midterms, I just want these levels. I will not look at the actual grammar syntax for C++. As long as you can tell me your ideas in this way, then I'll be okay. Okay? It would be great that if you can follow the styling of your textbook. It's easier for me to look at. Answer to chapter 4, exercise 1. If you're interested, let me just read it, it's okay. In each iteration of do-while loop, amount of added to elapsed time may deviate from actual runtime to something by up to 100 milliseconds or 100 ticks. Let's add our additive. Let's keep adding some overhead because we're doing this for 1,000 times. Over the iterations, so it does not decline as a fraction of the total time. For example, suppose do something takes almost 100 milliseconds to execute. In worst case, the clock reading will change just before each execution of the assignment, blah, blah, blah. Amount of time elapsed is 0 on each iteration of the do-while loop, and do-while loop does not terminate. We have no idea what they try to say. Take a look at the chapter 4, exercise 1. Read that question, and then try to match this up. I'm assuming you will take a look at the exercise 1 by next week, and we can come back to this for if you have more questions. 숙제를 안 물어봐서 다행이죠. 그냥 답을 줘서. 아마 답 거기 있을 거예요. 아마 exercise 1 아래. Unix, time my program. Time is another way of doing clocks. 왜? 질문? 아니야. 깜짝이야. So see man page for time, just like man G++, man time. Whether see what kind of formats they're returning to you. So how can you use that in your programs as well? You can look at it as a function. When we're discussing in the very first class doing a review for C++C, they usually say public operations and definition of the class. Now you're starting defining your own class, like it's already there, but assuming you're writing on your own, you will define something like linear list in order to construct an array structure in it. And these are the functions that you need to create or understand. So each chapter will give you like these ones. And we also covered the concept of inheritance too, right? So some chapters, later chapters will inherit these functions and build their own structures. And usually this type of stuff, 아이고 어려워 보이긴 한다. 갑자기 나가니까. 아니다. Let's do this in next class. Before I let you go, I need to call your names first. 좀 조용히 해요. 내 출석 부를게.